Hello, this is part 2 tutorial on how to use the Gadget for hybrid simulation code. So in the previous part, we made a linear response embodied simulation with all the neutrinos tracked by multi-fluid linear response. So now we want to take a part of the neutrino distribution and convert them into particles. So let's first look at the linear response results. So here, remember the folder that we used previously. And now we see an additional folder output has been created with the simulation data. So in this output folder, you will see a list of snapshots that corresponds to the list of output redshifts that you requested in the outputs.txt file. And there are also several folders containing other information that will be useful to us. So firstly, we need to look at the neutrino stream data. So this is the neutrino stream data. Okay, so this contains a list of all the files for both the delta and the theta for the neutrino streams in the multi-fluid linear response. And it will correspond to all the outputs that the snapshots have been written at. So we pick the time that we want to convert at. So for example, here we want to convert at A of 0.1 or redshift of 9. Then if you open the neutrino delta file at 0.1, then you'll see a whole list of data. So these are coming rows corresponding to the k values, and also each row will have one column for the k value, and then n tau number of columns for each of the neutrino streams. So the first one will correspond to the delta of stream 1 for this k value, and the next one will be stream 2, stream 3, and so on. And you'll have this for the whole list of all the k values that the embodied code computes, or the embodied code tracks. And you find the same thing for the theta file. So here you get exactly the same format. So one column for the k values and an n tau number of columns for each of the streams theta. And we're gonna download these files and use them to produce power spectrum and growth rate files for the initial condition generation of the neutrino particles in the conversion run. So here I'll go back to the output folder and now move on to the power specs folder, which is also useful for us. So this folder contains a list of text files where it's the power spectrum estimated of the particles inside the embodied box. So since we're running a linear response run here, so these will just be the CDM and baryon power spectrum. And they're not labeled, but you can correlate the numbers to the list of outputs that you've requested in the outputs.txt file. So for us, when we're looking at converting a Z of 9 or A of 0.1, it will correspond to power spec 001. And inside you'll see the usual Gadget 4 power spectrum output format. So, okay, so we're gonna first download the information from these two folders and reprocess the information a little bit just to form them into initial condition files that we can then feed into the hybrid run. So here I've downloaded them into my laptop with the power specs and the neutrino stream data. And I run this through a Mathematica notebook, but you can use any other program that you wish. So now, because of the change in the initial condition format, like I mentioned in the previous part, where we no longer need to do the log-base 10 formatting, where you can simply input the NPC on H cubed power spectrum for the initial conditions, this step is actually quite easy. So I just input the delta for neutrinos and the theta for neutrinos, and also the power spectrum estimated. And then I'll just make sure they match up to and then make two columns and then output the data in two columns in the exact same format as the linear response initial conditions, but this time for the neutrino data. So overall you'll need three files in this case. So you have the growth rate file for the neutrinos, where same as the linear response, we have one column for k separated by white space and then f of k. And then you also have one file for the power spectrum input for the neutrinos. So you have a column for the k, y space, and then p of k. Now this, since we're in this example, only converting the slowest stream, so stream 1 out of 20. So this power spectrum file for the neutrinos is prepared simply by taking the neutrino stream data, the delta file, and then extracting the column that corresponds to stream 1. If you're converting several streams bundled together into one batch and you need to average them, then you can do it similarly here. You can just do the sum of streams. Let's say going from stream 1 to stream 3. So bundle the first 3 streams together and then simply do an average. And you'll again get exactly the same format, except you will have the first 3 streams information averaged together. And you can do this in general for any number of streams that you wish to bundle together. But in this case, we're only converting stream 1, so we can just take the column corresponding to stream 1 and leave it at that. And the final file is one that's not present in the linear response simulation, and that is the power spectrum file of the particles that already exist in the box. So in this case, when we're going from the linear response to the first conversion, then we'll be taking the CB power spectrum. And again, it's the same format, so one column for K, Y space, and then P of K, or PCB of K in this case. In subsequent conversions, when you have both CDM and baryon particles as well as neutrino particles present in the box, you must remember this file has to be the power spectrum estimate of all the particles in the box, so not only the CB particles. So Gadget will estimate that for you, so you don't have to do any processing. You just have to find that power spectrum file that corresponds to all of the particles. Okay, so these 3 files will upload onto Katana and use for initialization. So here I made another folder called conversion 1 in demo. And you can see here it's pretty much the same as the linear response folder, where we have the outputs.txt, the params.txt, and the script file. And now we just have 3 rather than 2 initial conditions. And in the parameter file, I'll show you some stuff are now different. You now want to actually set the initial conditions. So the initial condition file is going to read the snapshot from the linear response run. So it's going to pick up where the linear response run left off in that snapshot and continue on, but now with particle neutrinos. So you have to tell it where to find it. So in this case, it will be in the linear response folder in the outputs, and then make sure you find the correct one corresponding to the redshift that you're converting at, and tell it exactly where it is. Right. So here, tell it go back, go to linear response, output, snapshot 001. There's one thing, you'll see that the snapshot file is called snapshot001.hdf5, but in this case, you don't want the .hdf5 in the actual file name. Gadget doesn't like that, so just keep it as snapshot001. Okay. The IC format here, you want to set it as 3. So setting this to 3 then tells Gadget that this is going to be a HDF5 format file, even though you didn't say anything here. So this is what tells it whether it's a HDF5, or if you set this to 1, then it will think it's the legacy Gadget format. 2 is the legacy Gadget 2 format, I think. But yeah, in our case, we'll always be using IC format equals 3, so that'll be fine. And the snap format 3, that just tells you that the simulation, when it outputs a snapshot, it's going to write it in the HDF5 format. So these 2 you can set, leave it always as 3 and don't have to worry about it. Okay, now time begin, we're now changing it to a higher scale factor, or like a lower redshift. So this will correspond to the starting time where we pick up from this snapshot. So snapshot 001 corresponds to redshift of 9, so we're starting at 0.1. Time max, you can set this to 1 if you want to only convert this one stream and then just want to see what happens. But sometimes with like subsequent conversions in mind, you don't have to run this all the way to the end. You can just run this to when you want to convert next. So in this case, I want to convert the next batch of neutrinos at Z of 7. So I can set the time max just at 0.125 of scale factor and not have to use too much computing power to go to all the way to the end. Okay, cosmological parameters, the CB omega density stays the same, the omega lambda stays the same, omega baryon stays 0. Now the omega neutrinos is going to be changed. So previously we had no particles, so this parameter is 0, and all of the neutrino density is in this omega nu lin. But in this case, we are taking out one stream out of 20 and putting them into particles. So that means we need to have a non-zero number here to tell Gadget that there are neutrino particles. And this should correspond to 1/20th of the total neutrino density fraction today. And if you're converting multiple streams, then this will just have to represent the correct fraction of the omega neutrinos that you're placing in as particles. And if you have done multiple conversions, then remember that this number has to represent all of the neutrino particles in the box, not just the batch that you're converting right now. So if I convert the next stream in the next conversion, then this will represent 2/20th or 1/10th of the total neutrino omega density. And omega nu lin will obviously be smaller now because some parts of it have been taken out, put into the omega nu part. So make sure these two parameters add together to give you the correct total neutrino density fraction. Gadget will not check, so this is kind of up to the user to ensure that it's correct. Gadget doesn't know exactly how many neutrinos or how much neutrinos you have in your cosmology in total. So make sure these two parameters add correctly up to the total amount. And everything else should stay the same. Hubble parameter, the box size, and NLR stays 2. Now in the n-genic part, now this is got additional parameters to take into account that we have more files to read in and there are more neutrino information that needs to tell the Gadget how to initialize them. So first thing that's different is that the grid size is now telling how many additional neutrino particles you would like to place in. So this 512 will say that I would like this additional stream of neutrinos that I'm converting to particles to be represented by 512 cube n-body particles. The seed is different now. So in the linear response run, the seed is used to generate the 3D phase of the density field. But in this case, we do already have the snapshot and thus the 3D phase is already determined. And the neutrinos will be following the CDM phase. So we do not need the seed table to generate the 3D phase again. In this case, this seed is used to generate the 0th order direction for the neutrino's thermal velocity. So this can be the same as the linear response run seed because it's used for a different purpose. So technically you won't have any kind of repetitive physical artifacts. But if you're converting multiple batches later and every time you do want to change the seed so that neutrinos don't end up, each batch of neutrinos don't end up with the same 0th order velocity drawn. Okay, primordial index is no longer relevant, so we don't have to worry about it. Although in reality, because the neutrinos, this is now the primordial index of the neutrino power spectrum, so it doesn't really get tilted anyway. So in the old version, you set this to 1 to make sure that it doesn't tilt the power spectrum. But in the new version, where it's not used anyway, so you don't have to worry about this. You can set this to whatever. Okay, and now we have an additional power spectrum file to read. So it's called CB power spec file. So that's the power spectrum of the estimated of all the particles present in the simulation before this conversion. And then we have the normal power spectrum file and the growth rate file as the linear response run. But these now correspond to the neutrino information. So the power spectrum file is asking for the converting stream's neutrino power spectrum. And the growth rate file is the growth rate of the stream that you're converting right now. And now we have 3 additional parameters as pertaining particularly to the neutrino conversion. So the first one's the stream velocity. So this is asking for the co-moving Lagrangian velocity of the stream that you're converting. So remember that when we computed the multipolar linear response for the growth rate and the growth factor, we got this list of tau t EV momentum. So that tells you the Lagrangian momentum in electron volts of each of the 20 streams or n tau streams that you have. So we have to convert this to units of kilometers per second for inputting here. And so you can do this easily by just taking the mass of neutrinos, speed of light, and the velocity in kilometers per second will be the Lagrangian momentum divided by the mass times by the speed of light and then divided by 1000. So here I just took the list of all 20 streams and the Lagrangian momentum in the EV and converted into here a list of 20 Lagrangian velocity in kilometers per second. And we're converting only the first stream, so we're taking only the first stream's Lagrangian velocity. So 361 kilometers per second, and you put it here. And the next two are n tau pi and nu pi deg. So new part deg stands for neutrino part degeneracy, and the first one is how many streams are particles. So the first one is asking after this conversion. So after the gadget have converted this stream of neutrinos that we're doing here, how many n-bodied types of neutrinos batches there are in the box altogether. So after the first conversion, we will have one batch of neutrinos. So n tau part is equal to 1. If we've done 3 conversions, so this is the third conversion, for example, then we have 3 batches of neutrinos, then this would equal to 3. So this will be cumulatively counting how many neutrino batches have been converted into the simulation. And new part degeneracy now asks how many streams does each of this batch represent? So in our case, when we are converting only stream 1, then this would just be equal to 1. So saying that this batch only represents 1 stream, and that's fine. If I was averaging, say, 3 streams into 1 stream to convert as 1 batch, then I'll have 1 batch of neutrinos, but this parameter equal to 3 to represent that there are actually 3 physical streams averaged inside. So these 2 parameters will be important for telling the linear response code, how the linear response module, how many streams to exclude from the multifolder calculation, so you don't double count the particles and the linear response components. And right now in this implementation, once you converted a stream and once you converted 1 batch and you determine how many streams in the degeneracy, you have to actually keep the degeneracy fixed. So every stream has to be the same number of averaged, every batch has to include the same number of streams averaged inside. So now I made the decision to convert only 1 stream, n tau equals to 1 and n part deg equals 1. Then when I convert the next stream, I can't average more. I'll have to convert single streams, so stream 2 and 3 going onwards. Okay, and 2 more files it has to read in, and these are the files coming from the linear response run or the previous run that you paused at. So let's go back there and show you what they are. So in the linear response, in the outputs, we now also have this y_new folder. So this includes 1 data file for each of the Redshift outputs that you requested corresponding to the snapshots. What this includes is all the neutrino multifolder linear responses current state at this snapshot. So it includes every single streams, all the perturbation arrays, and bundle it all together into 1 big data file. The reason is that we don't want to reinitialize multifluid. We actually just want multifluid to read in the previous where it left off in the previous simulation and pick up from there. Because if you reinitialize the multifluid module and reinitialize the perturbations, they'll be purely linear again, and they lose any linear response or any kind of additional power pick up from responding to the nonlinear CB particles in the previous simulation. So this is like the snapshot for the multifluid perturbations. And we want the simulation to read in the one corresponding to the redshift that we're converting at, so it'll be this one. And then another folder is the delta grid. So in the delta grid folder, it includes 1 data file for each of the outputs that we requested again. And this one is the 3D phase information of all the particles in the previous box. So as I said, we want the neutrino particle to be initialized with the same phase as the particles inside the box. So this is how the gadget code in the conversion run is going to find out about the phase. So it's included here, and you want to read the file that's corresponding to the redshift that you're converting at, so it'll be this one. Don't try to open these 2 files, the delta grid or the y_new file. They are all binary and they're extremely large, so you can't really, there's nothing interesting or even readable inside. Gadget knows what to do with it, and you just don't have to bother looking inside, and you don't have to do anything with them. Okay, so that's what we're gonna put in. So in the parameter file here, make sure y_new file gets to the right path, finds the linear response folder, go to the outputs, and find the correct y_new at the redshift of the conversion. And same for the delta grid file. Go to the correct path and find the right delta grid file. Okay, and outputs.txt file sets the same as before, so we're outputting at the redshift that we're starting at, and also at the end of the run when we want to convert the next batch. The script file is the same as well. You just have to budget more resources. Again, it's hard to estimate a priori. You can use the Gadget 2 paper to have a rough estimate and just kind of over budget for it, because the multi-flow is going to use up some more resources, and also Gadget 4 just is a bit more resource intensive in comparison. Okay, and now the final thing is the Gadget binary. So I'm going to show you what options to put in the Gadget binary for compiling for a hybrid run. So in the new config file now, everything is pretty much the same as the linear response version. In particular, just remember to disable the lean option. Do not turn it on, because the neutrino particles will be initialized with variable mass, and lean option forbids that. So we want the lean option turned off to allow variable mass assignment. Periodic self-gravity, PM grid, set this the same as the linear response run to just keep consistent. You don't want this to be different and make it hard to compare later to the linear response versus hybrid comparison. And yeah, multiple order stays the same. The types of particles stays the same. The one change down here is that we're now turning off the create grid option. So we don't want the Gadget code to go create more CB particles. We only want to create neutrino particles. So now you turn on these three options called additional grid. That tells Gadget that we're going to read in the snapshot, have the CB particles read in, and then put in an additional batch of particles. And then turn on thermal velocity IC. That tells Gadget to give these new particles a thermal kick. And CB phase tells Gadget that these new particles do not draw a random phase for the density field, but read in the previous phase from the snapshot and from the delta grid file that we provided. Okay, and now you just have to make this file. I already made it and I copied it across, so it's fine. So again, you can either make it directly in the Gadget folder and CP the binary over to where you need it, or you can make it directly into a directory where you're going to run the code. Okay, so now we go back. And then we just have to qsub the script. And there you go, there's in the queue. So that's how you now run a Gadget 4 conversion run for the hybrid mode.